All right, so section 3.12, the photoelectric effect. You can sense that we're in a lab-themed mode here. This unit has a lot of things tying in labs that we're going to try and do a number of over the next weeks, whether in class or virtually, we'll see. But anyway, the name kind of says it all, right? Photoelectric. The prefix photo means light. Electric means referring to electron. Okay? The idea of the photoelectric effect is the idea that light, when it hits a clean metallic surface, can actually cause electrons to shoot off. It could actually ionize the metal to some extent. And because of that, there's going to be a specific amount of energy related with this process because it takes energy to remove an electron. We've talked about ionization energy already. So this ties into that idea there. And obviously different metals would require different frequencies of light in order to emit them because they have different ionization energies and frequency relates to energy. So we're back to those equations again. C equals lambda nu, where lambda is the wavelength, nu is the frequency, equals h nu, where h is Planck's constant and nu is the frequency. And just for sake, I'm going to assume that maybe you don't remember, c is the speed of light, which is 3 times 10 to the 8th. And I can't hit the, okay. Gotta move my screen down a little bit. Come on, move. Can't hit the buttons. Okay, 3 times 10 to the 8th meters per second. And h, Planck's constant, is 6.626 times 10 to the negative 34th joule seconds. All right, so it's not joules per second, it's joule seconds, because when you multiply that by frequency, which is essentially just 1 over seconds, you would get just joules. And technically it's a lowercase h. Okay, so those are constants. Those are given in your equation packet. These two are also given in your equation packet. This is not given in your equation packet, but I have no problem if you ever want to combine the equations and use it in that vein. Okay, all I did is, because nu or frequency is a common thing to both of these, I solve for it here and substitute it in. So very often I use this when I'm going between energy and wavelength. And the question doesn't ask about frequency, so why do I worry about finding the frequency? All right, so we need to understand these relationships a little bit, and you should be somewhat familiar with them already. All right, so let's take a look at some examples. Cesium only emits electrons when light with a wavelength of 652 nanometers or shorter shines on it. How much energy is needed to release an electron from cesium? All right, so we're talking about, again, wavelength, and we want energy. I could use the wavelength to find the frequency and then use the frequency to find the energy. But again, I like to use that combined equation. So I'm going to take Planck's constant and the speed of light, multiply them, divide by the wavelength. Now, keep in mind it was in nanometers. Nano means 10 to the negative 9th. So I'm saying 652 times 10 to the negative 9th. You could write it as 6.52 times 10 to the negative 7th, but I let the calculator handle that stuff. I don't worry about that. When I multiply it out, I get 3.05 times 10 to the negative 19th joules. Now keep in mind, that is joules per photon technically, because we're talking about for just one photon. That is a very important thing that you keep in mind, because this is a tiny amount of energy, right? Because we're only dealing with one photon. Most of the time, we're going to deal with large quantities of photons, so we're going to get a much larger amount of energy. So, with that in mind, based off of the PES diagram above, what wavelength of light in nanometers would be needed to emit the electrons from this metal? Okay, I'm forgetting a word there. All right, so we look at the PES diagram, and you have to remember that we're starting here. So this 1s2, 2s2, 2p6, 3s2, 3p1. Okay, so the metal definitely is aluminum in this case, but we're talking about this electron. Okay, this would be the first one to come off. So we want to know what wavelength would be needed to emit this guy out here. All right, so I know the energy is 0.58 megajoules per mole. Now, all of a sudden, whoa, mole, keep that in mind. That's important. We can't just ignore that. So what we're going to have to do is take that 0.58 megajoules per mole, convert megajoules to joules. Mega means million, so we have 1,000,000 joules for every megajoule. And I got to convert it to photons because we know a mole of photons is 6.02 times 10 to the 23rd photons. That's going to get rid of moles. We're going to be left with joules per photon. And that's really what we were working with in the previous example, is how many joules per photon. But we're going to just talk about one photon now and just work with that. So I did the conversion. I have my energy. Now I go back to the same equation, but I'm going to rewrite it because I want wavelength. So I'm going to say wavelength equals h times c divided by e. Notice that it's just wavelength and e that are swapping places. Makes this a little bit easier if you do remember it. So now I substitute in h and c are constants. The energy we just found in the previous part, I get 2.06 times 10 to the -7th meters. But the question did say express it in nanometers, so I have to multiply it by 1 billion. Okay, because there are 1 billion nanometers in 1 meter, and so I would get 206 nanometers. Okay, now let's just talk about that real quick. So roughly, where do you think that is? 206 nanometers in the electromagnetic spectrum. We said the visible light goes from 400 to 700. That's a smaller wavelength, which means it's got to have a higher frequency. So we've got to be in probably the ultraviolet range. Okay, so you need to keep those ideas in mind as we go through. All right, so there is the end of another small unit. Enjoy it and enjoy your break. Be safe, and hopefully I'll actually see you in school very soon. Bye, guys.